Hello everyone, welcome to PyLadies Con. I am Garima, your MC for this session, and I have the pleasure of introducing Sheila Ansai, our speaker who will be speaking on empowering sustainable agriculture, quantifying the impact of water resource management with Python. Sheila is a researcher who works along a group of scientists at Tetra Tech Center for Ecological Analytics and Modeling. Her current research involves around using data analytics, all that wrangling, to predict and minimize the human's impact on our climate at regional and national scales. In today's session, we will be focusing on ecosystem service market consortium's needs and the need of Python to develop a collaborative tool and the to quantify the impacts of water quality and water quality management. Thank you.
I'm Sheila Sai, and I'll be presenting on how we've been empowering sustainable agriculture by quantifying the impacts of water resources management practices with Python. This work wouldn't really be possible without partnership from our client, the Ecosystem Services Market Consortium, or ESMC for short. I'd also like to thank my colleagues at Tetra Tech for their hard work and support. So for this talk, I'm going to start with some background as well as motivation for the work that we did. Second, I'll walk through the Python Flask app architecture. Third, I'll discuss the key components of this Python Flask app. Fourth, I'll share some features that I think are really cool. And last, I'll discuss some lessons that I learned along the way. So I wanted to share a little bit about myself. I'm an environmental data scientist at Tetra Tech, and my background is in hydrology and environmental engineering. I'm especially interested in the movement of water across the landscape, what it picks up along the way, and how we humans can reduce our impact on water quantity and water quality. I'm passionate about coding in R and Python, but just going to focus on Python today because this is PyLadiesCon. So to tell you a little bit about ESMC, they're a nonprofit organization. They were founded in 2021. They facilitate collaborations between agricultural producers and people and companies in the food and beverage corporations. It's the best way to put it. And those corporations that are aiming to address the complex interactions between climate, biodiversity, and water challenges in agricultural landscapes across the United States. ESMC's mission is to recognize and reward agricultural producers for implementing sustainable practices like those that reduce greenhouse gas emissions, improve biodiversity, improve water quality, and reduce water use. So in this talk, I'm really just going to focus on ESMC's efforts to improve water quality. So we partnered with ESMC on this project to achieve three main goals. The first was that we wanted to automate spatially relevant water quantity and water quality calculations. Specifically, we wanted to allow them to be able to compare baseline conditions of an agricultural field to future conditions where a producer was potentially going to be implementing an agricultural best management practice. Second, we wanted to use an established scientifically grounded approach. And then last, we wanted to provide, in addition to water quantity and water quality calculations, other ancillary environmental data that ESMC could potentially use to summarize the results of the PLET module in context of, for example, a regional watershed. And this would be helpful for them as they are preparing data summaries and doing different reports of the programs that they're initiating and carrying out. So you might be wondering, how do we go about quantifying the water resource impacts of agricultural best management practices? So to do this, we leveraged an established application called the Pollutant Load Estimating Tool, or PLET for short. This was developed by the United States Environmental Protection Agency over 20 years ago. It's currently accessible as an Oracle database web application, as an Oracle-based web application shown in this screenshot here. PLET supports the quantification of agricultural water quality improvement activities like planting cover crops, reducing tillage, or establishing a section of grass and forest land that's downslope of an agricultural field. This is commonly called a vegetated buffer. The overall goal of many of these practices is to reduce the speed and amount of water that's flowing across the landscape. By slowing the water down and reducing its volume, pollutants can be kept out of streams. So overall, PLET helps to estimate pollutants like nitrogen, phosphorus, and sediment, and their loads to streams from agricultural lands with and without best management practices. So just to clarify the distinction, PLET is a web application that was developed and maintained by the U.S. Environmental Protection Agency, but the PLET module is the Python Flask app that we developed. It uses the U.S. EPA's or U.S. Environmental Protection Agency PLET formulas, so mathematical equations, and provides the back-end only water calculation capabilities for ESMC. So specifically, ESMC is incorporating the PLET module into their EcoHarvest platform. This platform allows agricultural producers to document the sustainable agriculture practices that they're implementing on their fields. So just to summarize, the mathematical equations behind PLET and the PLET module are the same, but we developed the PLET module, and that's what I'll be talking about in the next coming slides, specifically to meet ESMC's needs. So let's start with the PLET module's inputs and outputs. So in the real world, inputs represent a producer's agricultural field, along with information about the best management practices that they are going to implement in that field. So just looking at this example field here on the right, there are two fields, field 1 and field 2. And then the input GeoJSON file looks more or less like this table here with field ID, the best management practice to be implemented, the area of the field that the best management practice treats, and the geospatial information about the field. So those are all columns in the input GeoJSON file. And just for reference, a GeoJSON file is a special type of JSON file that has geospatial geometry data included. You can see that in the last column of the table, input table. The output table is the same. The first part of it is the same as the input GeoJSON, but it has a number of columns added to the end. The ones that I specifically wanted to highlight and that are included in this figure are they include information about pollutant loads from the field without the best management practice. This is the baseline condition, and with the best management practice. So this is called the practice change condition. And we also provide the percent change in these between the two conditions. So for example, if you're looking at field 1, where you're applying a cover crop, it's estimated, this type of best management practice is estimated to reduce phosphorus loads in runoff from the agricultural field by 85%. For field 2, if you implement a forested buffer, it's estimated using the PLET module that you would reduce phosphorus loads in runoff from the agricultural field by 60%. So the output, it's not included in this image here, but the output also includes other ancillary environmental data like the watershed that these fields are located in, the ecoregion description, soil information. Those are just some examples. So as I mentioned previously, the PLET module adapts the United States Environmental Protection Agency PLET mathematical equations to Python to meet ESMC's needs. So the PLET module is meant to be set up as a Python Flask app on a remote server. So here this would be ESMC's server. That hosts both the PLET module on the server, including the code and the static data sets. Then an administrator at ESMC runs a Python script on their local computer and passes that input file that has all the field information to the ESMC server. The PLET module runs, and then the user on their local computer, they get the output GeoJSON back with all those calculations appended. So I don't have time to walk through the public tabular and geospatial data sets that we use or all the details about them. But here's just a list of the notable ones: US Census data, soil data, US Department of Ag census data, including animal counts by county, land cover data, watershed boundaries, and ecoregion descriptions. Whenever possible, we used open source Python libraries. Here are just a few key ones. We use Flask for packaging up the PLET module as a backend application, Pandas for wrangling tabular data, GeoPandas for wrangling and analyzing vector geospatial data, and then Raster.io and RasterStats to analyze raster geospatial data, like the soils data or land cover data. So it's also important to make sure that the PLET module calculations were actually lining up with the United States Environmental Protection Agency's calculations. So to do this, we created a hypothetical GeoJSON file with agricultural fields, and then also it included all the other user inputs. We used that GeoJSON file as an input into the PLET module. We also manually entered the same information into the United States EPA PLET web application, and so we were able to compare those results. We found that the PLET module results were no more than 0.2% different because the two platforms rounded numbers differently. We are satisfied with the result. So there were really three things that I especially loved about this project. First, gave me a chance to practice writing tests to check inputs and outputs to the PLET module. Second, it was really fun. It was a fun spatial problem to automate the scaling of the animal counts from the county scale to an ESMC member field. This was a great way to reduce the number of variables that a user had to implement using a publicly available data set. Third, it was exciting to see how fast it would be for ESMC to implement the PLET module and run calculations for each field. So prior to this work, they were actually manually calculating these values for each field. So overall, it was a really fun and rewarding coaching project for me. There were 5 important lessons that I learned, and I just wanted to talk about each of them. So first, it was really important for us to functionalize the code that we developed, meaning that all the analyses we did were broken up into a series of custom functions. That helped us improve the readability of our code and also speed up the time it took to run. Second, I'm also like a fairly conservative user of large language models and AI, but I think it was really helpful to ask my favorite AI platform a coding prompt. And then especially, when I was really stuck with the coding problem or didn't understand an error message. So using those resources was helpful. Third, it was really important for us to collaborate on Git and GitHub to make sure that all staff were working with the same versions of Python scripts. In some cases, I had to give some mini Git and GitHub tutorials, but it was really well worth the extra time spent doing that to keep everyone on the same page. Fourth, documentation takes time, but it was really important for my future self and also for our collaborators. And then last but not least, it's really good to remember to keep calm and carry on coding. So I really try to approach coding as a way to explore and learn new things. Sometimes I do get frustrated. So in those instances, I just try to remind myself to take a break or maybe ask my AI friend or my colleague for help. So yeah, thanks again for taking the time to watch this video. If you have any questions, feel free to save them for the in-person PyLadiesCon event or reach out to me at the email listed here. Thanks.
So, quantification and Python, they both go hand in hand. This session was a really informative one. Thank you, Sheila, for your session, and I hope you all got enjoyed it. Thank you.